Well, here are the answers to the quiz on interference. And there are only 10 questions here. And in the first question, light from a 600 nanometer source goes through two slits, 0.080 millimeters apart. What is the angular separation of the two first-order maxima occurring on a screen 2 meters from the slits? So you have the wavelength in nanometers. You have the small d, which is the distance between the two slits. And it says you have to find the angular separation of the first two maxima. And the screen is 2 meters. Alright, so that's lambda, 600 nanometers, times 10 to the negative 9 in meters. D, 0.080 times 10 to the minus 3 in meters. M is 1. I'm talking about the first order now. The distance is 2 meters, and we use d sine theta is equal to m lambda and find sine theta. On substitution, you get sine theta as 7.5 times 10 to the negative 3, from which theta is 0.43 degrees. And therefore the angular separation must be 2 theta, because it's asking about the two first order maximas. It should be 2 times 0.43, which is 0.86 degrees. So the answer is A. On to the second one. A soap bubble has an index of refraction of 1.33. What minimum thickness of this bubble will ensure maximum reflectance? So that means it's talking about brightness. Maximum reflectance of normally incident 530 nanometer wavelength light. Okay. Refractive index 1.33, wavelength is 530 nanometers, again 530 times 10 to the negative 9 meters. And you're asked to find the minimum thickness. The condition here is 2t is equal to, before I write that, look at this diagram carefully. And so now you see the rays getting reflected. On the top, the first one is reflected as well as refracted, and the refracted part is again reflected and then comes out. So these are the two rays that are going to interfere. And therefore, if the thickness of the film is t, you know that the path difference between them is going to be t plus t, which is 2t. And for brightness, it's air inside and outside, and that's the soap film. And why did I put lambda by 2 there? Because remember, whenever reflection takes place, when it's trying to go from less dense to more dense, it jumps in path by lambda by 2. So there's an additional path difference of lambda by 2 here, which this one does not have. Why? Because it's getting reflected while it's trying to go from more dense to less dense. And that is why the condition for brightness now is actually 2nt is equal to m lambda, but I got to take away lambda by 2. So that makes it lambda times m minus half. So from here we can calculate the thickness. Just rearrange the terms. And if it says minimum thickness, then you got to put the lowest value of m, which is 1. And so minimum thickness would be lambda by 4n, because when you put this as 1. Oh, when you put the value here as 1, you're going to get half here, and so you have 2 times 2 is 4. Okay, substitute the numbers and you get the answer. This is still in nanometers because I've just put 530 there, so the answer is 99.6 nanometers. Number 3. There's a thin layer of oil on top of a puddle of water there, and light is normally incident, wavelength 500 nanometers, strongly reflected. So again, condition for brightness. So what is the minimum thickness? Just like the previous problem, but maybe with a small difference. All right. So the light is reflected and refracted as before, but now you have air, oil and water. So in the first case it's trying to go from less dense to more dense, that's here, and in the second case again it's going from less dense to more dense. Okay, so in both these cases there's an additional path of lambda by 2. So actually it cancels out. So when we go for the condition for brightness, it remains as m lambda. And from there you calculate the thickness. Once again, if it says minimum thickness, then m is 1. And when you substitute, you get 200 nanometers as the thickness of the oil film. That brings us to number 4. Here you have light of wavelength 550 nanometers traveling at 1.96 times 10 to the 8 meter per second in a certain liquid. Find the wavelength of the light in the liquid. See, the wavelength in a material of refractive index n is always the wavelength in air divided by the refractive index of the material. So when you rearrange, and you know that refractive index is defined as the speed of light in air divided by the speed in that material. So you can find the refractive index first. Get is 1.53, and then all you got to do is 550 divided by 1.53. It gives 359 nanometer. In the fifth one, it's a monochromatic source, shines through a double slit onto a screen 5 meters away. The slits are 0.18 millimeter apart. The dark bands, be careful, now it's talking about the minimum. The dark bands on the screen are measured to be 1.7 centimeter apart. What is the wavelength of the light incident? Okay, so that is the diagram of interference. That's the distance between the slits and the screen. X is the distance from the center to the fringes, and we know the condition is d sine theta is m plus half lambda because it's darkness. On rearranging that, you get sine theta is m plus half lambda by d, and also tan theta is x divided by the length, I mean by L here. How? Because from this triangle definitely tan theta is x by L. Yeah, so you have two conditions, and remember, when theta is small, sine theta is equal to tan theta. So the left hand sides are equal. Put the right hand sides equal to each other, which I'm doing now. And make x the subject. So now I'm saying if that's what you get for the mth dark band, then for the m plus 1th one, all you got to do is in place of this m here, just put m plus 1, right? So that's what I'm doing here. So that makes it m plus 1 plus half, and that gives you m plus 3 by 2. So you have two equations, and if you want the distance between them, you got to take the difference between them. So I'm going to take away this quantity from here. And the right hand side, if you watch carefully, you're going to get lambda L by D. Why? Because you have 3 by 2 and 1/2, right? 3 by 2 minus half is 1. One of the terms, the first term is going to get cancelled when you distribute, and that's what you get. So rearrange and you get lambda. You have all the terms now, and you would calculate the wavelength. Remember, all of these quantities are in meters now. And since the answer is given in nanometers, that's 612 nanometer. There you go in number 6. Again, a 2-slit experiment. The slit separation is given. The interference pattern is created on a screen 2 meters away. The 7th bright fringe is a linear distance of 10 centimeters away from the central fringe. What is the wavelength of the light? This is a direct question where you just have to substitute into the equation. And just as before, sine theta is equal to tan theta, we did all this before. And so finally, when you put them together, you get lambda is equal to x by m times L, and when you substitute, x is 10 centimeters, that's why it's 10 times 10 to the negative 2. It's the 7th bright fringe. Once again, remember, we're using the condition for brightness. And in nanometers, 214, yes, nanometer. The 7th one, light of wavelength 575 nanometer falls on a double slit, and the 3rd order bright fringe is seen at an angle of 6.5 degrees. What is the separation between the two slits? D sine theta is m lambda. It's talking about bright fringe, and you got to calculate D. M is 3, lambda is given, change it into meters, sine of the angle, and you have the answer. If it's in micrometers, it's going to be 15.2 times 10 to the negative 6. So micrometers, it'll be just 15.2 micrometers. 8th question, again a Young's double slit experiment. The separation between the slits is given. The distance from the slits to the screen is given. You got to find the spacing between the 1st order and the 2nd order bright fringes, wavelength given. Now, one of the other questions we already found out, and that was question number 5, that I'm using a new symbol now to give the bandwidth. That's the spacing between any two dark or bright bands. And you can learn it as lambda times the length divided by D. So that's from question 5, and that's a general standard equation. Calculation gives 3 centimeters as the spacing between the 1st order and the 2nd order bright fringes. 9th one, slit separation 2 millimeter. The wavelengths, 2 wavelengths now, are falling on the slits. Screen is 2 meters away. Question is, at what distance from the central maximum on the screen will a bright fringe from one pattern first coincide with a bright fringe from the other? So you have 2 cases now. You have 2 wavelengths. You have 2 cases, but their thetas have to be equal. Why? Because it says it should coincide. So the thetas are equal. We have this formula for, it's talking about brightness, so make x the subject. Now x must be the same, and D and L are the same. Therefore, from that we know the product M1 lambda 1 should be equal to M2 lambda 2. Yes. It's simply a ratio question now. M1 is M2 plus 1 because the problem says so. Bright fringe from one pattern first coincide with a bright fringe from the other. You know, we know that it cannot be the same ones, okay, from the other. Why? Because one wavelength is 750, the other is 900, and if you look at the product, you understand that it's going to be the next one from the 750 that's going to coincide with the one from 900, okay? So on solving that, you get M2 as 5, which means you can put it back into this equation here and find out what X is. (4.5) times 10 to the negative 3 meter, which is 4.5 millimeter. Alright, now the last question. A monochromatic light is incident on a double slit setup. Slit separation is 30 micrometer. The resultant bright fringe separation is 2.15. The screen is 1.20 meter away. I was just trying to show you how the slits are, how the bands are, you know, the dark and bright bands on the screen. And it's asking you what's the separation between the third order bright fringe and the 0th order bright fringe. So I have the 0th order and the third order bright fringe. And the separation is going to be 3 times the spacing between any two, right? And here beta is 2.15 given. So the answer should be 3 times 2.15, and you don't need any of those other steps, which is just being smart. If the distance between any two adjacent ones is 2.15, then of course the distance between 3, so it's just 3 times 2.15, the answer is 6.45 centimeter. Thank you, and take some time to understand these answers. Good luck.